understand the on-chip clock controller IP operation, we'll talk about the different OCC controller should be inserted. The first option is -cell name, which is the instance name for the IP once it is inserted. Secondly will be cycles per clock. First up, let's talk about at-speed testing. Delay-related defects are physical defects that logically behave as a transition delay. For such defects, a stuck-at pattern set will not fail in the presence of this type of defect. In order to catch the delay-related defect, these two conditions are required. First of all, the pattern should generate a transition at the fault site, and secondly, the effect of this transition should be captured at speed. How would you handle multiple internal clocks? So internally generated clocks can be handled using one of these two ways. First of all, you would bypass these internal clocks with an external clock. This is used for both shift and scan capture. Alternatively, you could implement a clock controller or on-chip clock controller or OCC to use the internal clocks for at-speed clocking during scan capture, where it will be shifted slow, but the capture will be at speed. The problem with using a single external test clock is it will create setup and hold time issues for scan mode, shift, and capture. For smaller geometries, the process variation can make it impossible to close timing on a single test clock. This makes at-speed ATPG very difficult. Therefore, you may need elaborate flop masking, which causes pattern inflation. Also, there's no independent control of at-speed clocks. To solve this, one option is to use a separate top-level clock for each clock tree synthesis tree if possible. This eliminates the need to fix setup or hold time issues between CTS trees that have different latencies, and it also allows simultaneously testing of multiple frequencies at speed. Alternatively, you can use multiple OCC controllers to give ATPG separate controller for each clock domain. This way, it allows you to simultaneously test multiple frequencies at speed, and there's no independent control of internal clocks for stuck-at ATPG. The third way is to use separate OCC ATE clock sources, where possible. This allows simultaneously testing of multiple frequencies at speed, and it provides independent control of internal clock domains for both stuck-at and at-speed ATPG. The issue with testing at speed using external clocks: the capture speed is limited by the tester clock speed, as well as is limited by the I/O path. With multiple internal clock domains, this will require multiple external clock paths. So where path-limited designs, where you're going to have a scan clock that is collapsed, at-speed testing becomes unsustainable. Also, testers that can generate at-speed ATPG with external clock sources can be very expensive. The better solution is to leverage existing PLL clocks for at-speed ATPG. So the question is, how do you leverage existing PLL clocks? The solution is to insert on-chip clock controller, and Fusion Compiler DFT supports the insertion of such OCC logic. The requirements of this OCC are as follows. It should allow you to switch between a slow external clock for shifting and fast on-chip clock for at-speed capture. It should allow you to synchronize between the fast and slow clocks. It should allow ATPG to control the fast clocks to the core on a per pattern basis. And lastly, the hardware should avoid any glitches. Here's an example on-chip clock controller. The on-chip clock controller should be inserted between the free running or PLL clock and the registers that is being driven by this PLL. A separate clock chain with all the bits is used to control the on-chip clock controller, and this clock chain is controlled by ATPG. The on-chip clock controller block should be placed after each internal clock generator, PLL, or any free running clock source. There are no restrictions on the number of on-chip clock controllers being supported, and there's full automation between DFT insertion in Fusion Compiler and downstream ATPG in TestMax ATPG. The ATPG tool will then decide per pattern which clocks should be posted. The tool supports a mixture of on-chip clock internal and external clocks. There's no inter-domain testing between internal and external clocks. The internal clocks are asynchronous to the ATE, so the relative timing is unpredictable. Next up, we'll talk about the on-chip clock controller IP. The OCC logic inserted by Fusion Compiler DFT supports these modes of operation relating to the on-chip clock. First and foremost, the functional mode where the on-chip clocks are used. Second of all, there's a bypass mode where the external clocks are used for both shift and capture. There's a scan shift mode where the external clocks are used, and the at-speed capture mode where the on-chip clocks are used. On SolveNet Plus, there's a datasheet that describes the Synopsys on-chip clock controller IP. The following diagrams show the operation of the on-chip clock controller in detail. First, in functional mode, the OCC test mode 0 selects the fast clock and feeds it onto the registers that are being driven. In OCC bypass mode, both the PLL bypass signal and OCC test mode are asserted to 1, leading to the slow clock from the ATE being selected to send to the registers downstream. In the OCC mode for scan shift, test SE is set to 1, PLL bypass signal is set to 0, and OCC test mode is set to constant 1, thereby selecting the ATE slow clock to send to the downstream registers. For OCC mode in at-speed capture, test SE is set to 0, PLL bypass is set to 0, as well as OCC test mode is set to constant 1, therefore selecting the fast clock from the PLL. Here's the waveform for the on-chip clock controller, and it illustrates the synchronization operation between the ATE clock and the PLL clock. In normal scan shift, the scan enable signal is active, therefore the slow ATE clock will be enabled. When scan enable signal falls, the slow clock first synchronizes to the fall of the scan enable, then the fast clock. Once the fast clock gets a hold of the scan enable signal, it passes through a metastability shift register and onto the counter. There are 3 synchronization cycles for the PLL clock to pulse for capture to prevent metastability. According to the clock enable settings scanned in by TestMax ATPG to the clock chain, some of these high-speed pulses will be output from the controller. After this, the system stops and waits for the next event. When scan enable comes active, again from the ATE, it gets synchronized by the high-speed clock and by the ATE clock, and the results are shifted out while shifting to the next pattern. With multiple OCC controller, ATPG will use the clock chain bits to control which OCC clocks are pulsed for each pattern. The pattern will shift through the clock chain, and each PLL controller will be activated by the corresponding clock chain bits. Next up, we'll talk about the OCC insertion flow in Fusion Compiler. Fusion Compiler DFT supports an OCC insertion flow or an OCC identification flow, but not both in the same flow. Fusion Compiler DFT can insert 1 or more OCC blocks. The on-chip clocking logic is inserted for the specified clocks. Insert DFT command will then synthesize this on-chip clock controller. All the flip-flops that receive the OCC clock will then be scanned, and the test protocol file is generated for both on-chip clock as well as on-chip clock bypass modes. For the identification flow, FCDFT can identify 1 or more existing on-chip clock blocks. This logic has to be already existing on the specified clock. The existing on-chip clock logic is recognized by FCDFT. Afterwards, all the flip-flops that receive the on-chip clock will be scanned. Then the test protocol will be generated for on-chip clock and on-chip clock bypass modes. For OCC controller insertion, the placement of the on-chip clock controller lies at the output of the free-running clock. If the free-running clock from the PLL directly drives registers, typically you will need to insert an anchor buffer to give the on-chip clock logic a place to be inserted. If you have multipliers or dividers, the output of these can be used as on-chip clock insertion points. Here are the definitions of the clock signals surrounding the on-chip clock. First one is a reference clock. This is the frequency reference to the PLL. This is free running, otherwise the PLL may lose synchronization. A reference clock cannot be routed directly to the downstream flip-flops. Second is PLL clocks. This is the output of the PLL. This is also free running, that also runs at a constant frequency which may or may not be the same frequency as the respective reference clock above. Number 3 is the ATE clock. This shifts the scan chain. The ATE clocks are only used and routed to the respective OCC controller and cannot be routed directly to the clock inputs of the registers. Internal clocks is where the OCC generates for gating and selecting between the PLL clock and the ATE clock to generate the internal clock. So these internal clocks are the output of the OCC. Lastly, the external clocks are primary inputs that clock the flip-flops directly or through combinational logic. These are not generated from the PLLs and cannot be used or declared as the reference clock. So let's look at the commands to define each of these clock signals. First of all, the reference clock is defined using the DFT signal type ref clock. You need to provide the timing and the period. The ATE clock is the shift clock and is also paused during capture. To define the ATE clock, use the signal type ATE clock. The signal type PLL clock is used to specify where the on-chip clock controller will be inserted into the design. So, in this example, each of the output pin of this PLL is defined as the PLL clock, and the source of the PLL clock determines where the on-chip clock controller is inserted. The OCC test mode signals controls whether the OCC is in functional or test mode. To specify this, use the type test mode as well as the option -usage OCC. This is different from a test mode signal used for compression multiple mode scan, and you cannot share this with the other usage type. The OCC test mode can be internally generated as long as the signal can be set during the initialization and be held static. The PLL bypass signal controls whether the on-chip clock controller is an OCC or bypass mode. Specify using the signal type OCC bypass. Again, it can be internally generated as long as the signal can be set during initialization and then held static. The OCC reset type is used to initialize the OCC controller during test setup for OCC mode. Use the signal type OCC reset. This must only be toggled during initialization in OCC mode, then held inactive during ATPG. Now that the signal types have been defined, use the command set DFT clock controller to specify how the OCC controller should be inserted. The first option is -cell name, which is the instance name for the IP once it is inserted. Secondly will be cycles per clock. This is the number of fast clock pulses that the controller can generate. The -PLL clocks option points to the list of PLL clocks that you have previously defined. The -ATE clock option points to the ATE clocks that will drive the controller. The -test mode ports option points to the test mode signal used to switch between functional and test mode. Here's a script example and a schematic diagram that shows the design before and after insert DFT and what is being inserted by using the script to the right. You can pause this slide to study this diagram in detail. The test protocol written out by the write test protocol command contains both OCC active and OCC bypass modes. The active mode is determined by referencing a pattern exec block in the test protocol file. The name of the pattern exec blocks are based on the test modes that have been defined. Where the OCC bypass comes in, the pattern exec appends the string OCC bypass to the test mode name. Here are the blocks of patterns and pattern execs in the test protocol for OCC. You can see that the separate patterns for when the OCC is used and the OCC is bypassed. This protocol can be used in testmax ATPG by specifying the -pattern exec option for the run_DRC command. The test protocol also contains references to the clock structures. You can open the test protocol file with an editor and see where each of these signals are referenced in the clock structures block. Next, let's look at some of the OCC implementation options. In Fusion Compiler, the on-chip clock controller uses a latch-based clock gating logic for glitch-free selection between the fast and slow clocks. There's a SolveNet article that talks about the combinational and latch-based clock selection logic structures. You can use the following app option to specify a library cell for clock gating within the controller. For example, if you need to choose a specific integrated clock gating cell from your library, use this app option to specify it, and the tool will use it. By default, a clock chain clock connection shares the first functional clock output of the OCC controller, so this will put the clock chain in both the PLL and ATE clock paths. If you want to use a dedicated clock chain clock connection from the OCC, specify this app option. What this will do is it will create a dedicated on-chip clock controller clock output for the clock chain. It is placed in only the ATE clock path, which prevents it from affecting the high-speed PLL clock path. After inserting the OCC controller logic, it must be properly constrained for timing analysis. If you're using latch-based clock gating, the prime-time gated clock checks would work automatically, and there's no user guidance required. The latch-based clock gating removes sensitivity to the duty cycle of the PLL clock. To summarize, we have talked about how OCC facilitates ASPEED testing. We talked about the operation of the OCC controller IP. We listed the different types of clock signals used in OCC flows, and we've described the two primary OCC flows supported by Fusion Compiler DFT.
Hello, welcome to Module 11 of Fusion Compiler DFT Synthesis Training. In this module, we will discuss flows related to DFT-Max compression insertion. In this module, we will discuss which steps in the DFT flow are involved with adaptive scan insertion or DFT-Max compression insertion. We'll explain how DFT-Max compression maintains test coverage while reducing test application time and test data volume. Lastly, we will modify a scan insertion script to include DFT-Max Ultra compression insertion. Let's talk about the basics of scan compression. The motivation to use compression is due to semiconductor geometry getting smaller and smaller, while at the same time trying to maintain or even reduce the cost of test. At 130 nanometers or above, stuck-at fault and some transition delay were sufficient to detect manufacturing defects. As semiconductor geometry goes smaller, new manufacturing defects come into the picture, and additional tests are required to help detect them. These tests will include transition delay tests as well as testing such as bridging fault tests. These can easily increase the test time and test data by 6 to 8 times, well beyond the memory limit of testers. By utilizing compression technologies, we're able to reduce the tester cycles that are needed to perform the same tests, therefore maintaining the quality while reducing the time needed to perform manufacturing tests. This is a high-level diagram to show how compression works. Traditional scan chains are split into shorter chains, and shorter chains require less time to load and requires less data on the tester. So for example, we have 5 chains in this traditional scan design. Each chain perhaps would have 1,000 registers. Therefore, it would take 1,000 clock cycles to shift through a chain like this. With compression, we're able to split the scan chain into much shorter segments while sharing the same top-level scan-in and scan-out ports. Therefore, we reduce the number of clock cycles that are required to shift through the chains. The two main metrics in utilizing test compression are test application time reduction and test data volume reduction. The test application time reduction is used to calculate how much the tester execution cost has been reduced. Test data volume reduction is used to ensure the test program resides within tester memory. This is because tester memory is finite, and any time that is needed to reload a test pattern consumes a lot of time. And it is used if more patterns are needed to increase the test quality. So in this example, test application time is simply the patterns for the design multiplied by the scan chain length. So let's say we have a design of 2,000 patterns, and if it requires 1,000 cycles to load a pattern, this will result in a 2 million cycle test application time. By splitting the chains into 40 internal chains of 100 flops, by very nature, compression could result in pattern inflation. However, the number of cycles needed to load a pattern has been drastically reduced, resulting in just 240,000 cycles to load the same number of tests. Therefore, the test application time reduction is now at 8.33 times. It is typical for compression insertion to create at least two test modes. The first one is internal scan mode, which will reconfigure the scan chains to look like traditional scan chains. What it means is the short compression chains are just reconfigured into the longer chains. Many users refer to this as a reconfigured scan mode. Sometimes they call it fallback mode. Others may call it regular scan mode. The other test mode inserted by the tool is commonly known as scan compression mode. This uses the shorter chains directly. So the scan data will come from the top level port through the decompressor directly through the short chains, and then scanned out through the compressor to the chip. Many users will call this compressed mode. If they're using Synopsys compression, sometimes they will call it as DFT Max mode, or perhaps if they use DFT Max Ultra, it will be called Ultra mode. In a typical DFT Max insertion run, two new test modes are created: scan compression mode and internal scan mode. The default flow, the compression and regular scan modes are created automatically during insert DFT. All the scan-ins, scan-outs, and scan-enable ports are shared by both internal scan and scan compression modes. If you want to create dedicated multiple test modes, this will require an explicit specification of compression and regular scan modes. Using the multi-mode commands, the DFT specifications can be set directly on these modes prior to scan insertion. In order to switch between the internal scan and scan compression mode, we will need to utilize a signal of dash type test mode. Note that this signal cannot be shared with another signal that switches the design between functional operation and test. So in this example, the port T-mode 2 is used as the control signal to differentiate between internal scan and scan compression mode. whereas with port OCC test mode is used to switch between clocking using the OCC signal versus a direct external clock. All the information needed for testmax ATPG about compression architecture is contained in the test protocol file for compression mode. This test protocol file is generated by Fusion Compiler DFT during the DFT insertion step. Once you have finished DFT insertion, you can write out the test protocol using the write test protocol command, specifying the -test mode option and point to scan compression mode. Once the test protocol is written to file, the pattern generation flow with compression mode is the same as for regular scan. One thing to note is be sure to write out the compression mode test protocol from Fusion Compiler. This protocol file cannot be rebuilt later just by reading the Verilog netlist. If the post-DFT database in the NDM format is available, the test protocol can be written after opening the NDM. One recommendation is to only implement the level of compression that is required to meet the test requirement for the design. The more compression you add, other factors come into the picture, such as area overhead and congestion. Increasing the compression from 50x to 100x would reduce the test time by only 1%, whereas just a little bit of compression up to 10x, you will achieve already 90% of improvement. Now let's cover DFT max compression. DFT max scan compression, or known as adaptive scan, is built into Fusion Compiler. It's as easy to implement as scan. You just need to add an additional command into your script, and the tool will automatically insert the necessary logic to perform compression. You can select the compression ratio. There's virtually zero impact on the timing, and there's known to be a very low area overhead. In the basic shared scanning architecture, you have a top-level scan-in port that drives internal scan chains. Scan register in the same shift position on each of the chains will always be loaded with the same data. This creates data dependency and could limit the ability to test some faults in the design. The load decompressor selects a chain configuration where the scan data that feeds the AND gate are not driven by the scan in. This breaks the data dependency and allows for the AND gate to be fully tested. DFT max compression takes some of the scan inputs and uses them as control logic. From the tester point of view, the stimulus all looks the same, and you as the user cannot distinguish between whether the ports are used as scan inputs or used for control. This reconfiguration is done on a shift-by-shift basis. An additional feature of DFT max compression is the ability to handle X's. In Fusion Compiler, the default is to generate this X blocking circuit, which provides full X tolerance without additional pins. These X sources could be static or could be dynamic, but by adding this X blocking circuit, there will be no drop in coverage. High X tolerance adds the masking logic that allows ATPG to selectively view a collection of chains on any shift. So we will still get the benefit of full observability on most shifts, but can fall back into a masking whenever we need it. Now that we discussed how DFT-Max compression works, let's talk about how to insert this using Fusion Compiler DFT. This is an example script using regular scan flow in Fusion Compiler DFT. By adding one additional command, you're able to configure compression insertion and generate the additional compression mode. After scan synthesis and DFT insertion, the additional test protocol for the compression mode is also generated by the tool. You will need the following to insert DFT-Max compression. First of all, specify the number of external chains that you need to insert for your design. Then specify the number of internal or compressed chains in either the using SESSCAN compression configuration -chain count, or specify it using the max length option. Note that scan compression is enabled whenever you specify SESSCAN compression configuration command. It is not necessary to explicitly enable scan compression using the setDFT configuration command like you do in Design Compiler. By default, when you specify compression to be inserted in the design, the tool will automatically create one internal scan mode and one scan compression mode. If there are different test modes that you wish to create for your design, use the command define test mode and SESSCAN compression configuration to specify additional compression mode parameters. The compression mode will use the same scan interface as the base mode. So in this example, we have specified 2 scan modes and 1 compression mode. You will need to use the SESSCAN compression configuration -test mode option to specify the compression parameters such as input, output, and the compression mode chain count. Here is a full script for a multi-mode DFT-Max compression. First, enable the general multi-mode flow. Specify the mode independent signals prior to specifying the test modes that you want to insert. Once you have defined the test modes, you can then specify the chain counts for each test mode, as well as the compression mode. You have the option to specify other parameters such as clock mixing for each of the test modes. For a bottom-up flow, the hierarchical scan synthesis flow with test models is supported by DFT-Max insertion, and the compression mode logic is inserted at the top level. So one thing to note is you need to make sure that enough chains are created at the sub-block to enable balanced chains at the compression mode. Next, we will talk about DFT-Max Ultra compression. The DFT-Max Ultra architecture improves upon the classic DFT-Max compression architecture. It allows you to use fewer pins down to one scan channel interface. It has superior ATPG quality of results since it has built-in X tolerance and a streaming bidirectional codec. It allows for faster shift speed since the codec is pipelined, has registered X-mask control, as well as the lack of a clock gating. In the DFT-Max Ultra codec shift operation, the green bit illustrated here enters the codec phase shifter and passes onto the core to the various core scan chains according to the latched codec mode. At the same time, the core is unloaded into the miser and values begin to stream out of the codec. When the next bit comes in, the first bit moves on to other scan chains. More unload bits come down into the miser signature. This continues until the entire pattern is complete. Once the load-unload process has completed, the data left in the tail will become the next pattern's control and mask. So at the end of the shift process, the codec control is latched into some control registers. These bits get latched when scan-enable transitions. This includes the codec mode and masking information for the pattern. The mode control bits control the load mode of the next pattern. The mask control bits control the masking of the current pattern unload. Next, let's talk about how to insert DFT-Max Ultra compression using Fusion Compiler DFT. The command is sesscan compression configuration with the added option -streaming true. This option indicates to the tool that you want to insert DFT-Max Ultra compression. The rest of the options, such as chain count or max length, or dash inputs and dash outputs, are similar to the regular DFT-Max insertion. The additional option required for DFT-Max Ultra is the dash clock option. You need to use the dash clock option to specify the clock signal that drives the codec. This signal must have been previously defined as a scan clock. In the preview DFT report for DFT-Max Ultra compression, the tool will print out additionally the clocks used for codecs. One is the decompressor side of the clock, one is for the compressor side. Additional information regarding the DFT-Max Ultra architecture can be seen by running the command streaming DFT planner after insert DFT. This gives more detailed information related to the DFT-Max Ultra architecture that has been inserted by insert DFT. These are the flows supported in DFT-Max Ultra. A top-down insertion is similar to a flat flow where the codec is directly inserted to test all the registers in your current block. A has flow integrates blocks that have previously been inserted with DFT-Max Ultra compression and will concatenate the scan data directly to the top-level port. You can also run the design using a mixture of scan logic and compressed cores. The tool will insert a codec that would test the top-level registers while at the same time connect the scan input and output of the compressed core directly to the top level. Next, we'll talk about some advanced compression topics. Fusion Compiler DFT can insert pipeline scan data register. Pipeline scan data registers are needed to handle the case where there are long wires between the scan chain input and the first flip-flop and the last flip-flop to the scan chain output. These delays can be reduced by inserting pipeline registers at the beginning and at the end of the scan chains. these pipeline registers will divide the long routes between the scan chain inputs and outputs into smaller wires and therefore help reduce the path delay. To enable the insertion of pipeline scan data register, use the option Set DFT Configuration -Pipeline Scan Data Enable. The two methods of pipeline scan data flows are as follows. Automatic pipeline register insertion using insert DFT command within Fusion Compiler, or insert DFT could connect the existing user-specified pipeline registers. You can specify the number of head and tail pipeline registers by using the Set Pipeline Scan Data Configuration command. Specify the number of stages needed for the head and the tail, as well as specify the clock signal that drives the pipeline registers. Also, you can specify different clocks between the head and the tail. When pipeline scan data registers are used in the compression flow, the head pipeline registers should hold their state or capture a constant value during capture cycle. This would help prevent unknown values from being captured in the head pipeline registers, which could propagate through the codec and into the compressed scan chains. In Fusion Compiler, the tool will use scan head pipeline registers and tie each register's output to its functional data input so that it can hold the state. Next up, how would you minimize the power inside the codec? The XOR compression tree is needed only during scan shifting for that codec's compressed scan mode, and at other times this compression logic is not needed, but it could still toggle when the tail scan flip-flops of the compressed chains toggle. To address this, the tool will insert gatings at the inputs to the XOR compression tree to eliminate this toggling activity and therefore reduce power consumption in the other modes of operation, such as internal scan. Another way to reduce power during shift with DFT-Max compression is to insert shift power control chains, or SPC. This additional hardware comes between the decompressor and the first register of the scan chains. By adding this additional chain, pattern generation will be able to select which scan chain to fire, and those chains that are not active will be filled with zeros, therefore reducing power during shift. To enable shift power control chains, or SPC, enable it using the command set scan compression configuration -shift power groups to true. You will need to create a dedicated shift power chain with a dedicated scan in and scan out. Specify using the command set scan path with the -class SPC option. With that, the SPC flops inserted by DFT-Max will be added to the SPC chain. You will also need to specify the clock to use for the SPC registers. This was required if you don't already have an on-chip clocking controller chain. There's an optional signal to disable SPC functionality when it's not needed. The signal type is test control. Once you have specified the signal, specify in the set scan compression configuration -shift power disable option to point to the signal. You can also specify the shift power control chain length by using set scan compression configuration -shift power chain length. Note that the length of the control chain should be less than the internal chain length. The recommendation is to give ATPG maximum control by giving the same length as internal chains. To summarize this module, you should now be able to state which steps in the DFT flow are involved in inserting DFT-max compression. You have seen how DFT-max maintains the test coverage while reducing the test application time and test data volume. And you've also seen an example script. Hello, welcome to Module 12 of Fusion Compiler DFT Synthesis Training. This module will talk about two advanced, discuss primarily wrapped design, the types of wrapper cells that Fusion Compiler DFT will insert, as well as configuring the core wrapper cell insertion and stitching up as wrapper chains. For multi-voltage flows, we primarily talk about what kind of capabilities exist in Fusion Compiler DFT, as well as reusing existing multi-voltage cells during scan synthesis. Let's first talk about core wrapping. Core wrapping is a methodology that provides both test access and test isolation during scan pattern application. In the core wrapper flow, a wrapper chain will be inserted along the I/O boundaries of core between the I/O ports and the core logic. These wrapper cells are inserted in the core level synthesis run, like this. And the two types of wrapper cells that are supported by Fusion Compiler DFT, dedicated and shared. Here are the two types of wrapper cells supported by Fusion Compiler DFT. By default, Fusion Compiler will insert a dedicated wrapper cell, which consists of a dedicated flip-flop that provides controllability, observability, and shift capabilities. If your design has existing boundary I/O registers, these functional registers can be shared with wrapper cell logic to reduce the core wrapper cell overhead. A shared wrapper cell replaces the existing functional register, providing equivalent functionality in functional mode. Next, we're going to talk about the modes of operation for a core wrapped design. First up is in-test, or inward-facing mode. In in-test mode, the patterns are applied to the inputs of the core and responses observed at the outputs of the core. We are testing inside this box in the core logic. If an inward-facing mode is not declared explicitly, the tool will create by default an wrap_if mode. The next mode is outward-facing, or what we call X-test. In this mode, we're testing the logic surrounding the core and isolate the core. So it is from the port boundary to the wrapper cell on the input side, and on the output side is from the output wrapper chain to the output ports. If an outward-facing mode is not declared explicitly, a wrap_OF mode is created by default. Optionally, the tool can create a safe mode, which drives safe values from the wrapper cells that have a safe value specified. A safe mode is declared automatically if any wrapper cell has been declared with a safe state. If a safe mode has not been declared explicitly, the tool will create a wrap_safe mode by default. Here are some of the commands related to core wrapper in Fusion Compiler DFT. First up, you will need to define wrapper shift signals. You can choose either a single wrapper shift signal, or you can have different separate shift signals for input and output wrappers. You will then have to define capture enable signals. Again, it could be separate between input and output, as well as an existing port to be used as wrapper clock. You can use the set boundary cell command to specify individual wrapper cell characteristics for specific ports. Let's say I want to have a dedicated wrapper cell for a particular port. You can use a syntax like this: set boundary cell, --class wrapper, --ports, put the name of the ports, the dash type specify as WC_D1 to represent dedicated wrapper cell, and I'm specifying a safe state of 0. To prevent insertion of wrapper cells for specific list of ports, you can define using set boundary cell --type none and list the ports that you do not want to have wrapped. To control the wrapper chain count, use the command set wrapper configuration -chain count. Let's talk about maximize reuse functionality in Fusion Compiler core wrapper. The default core wrapping flow adds dedicated wrapper cells when functional I/O registers are not directly connected to I/O ports. However, you can save timing and area impact of core wrapping by utilizing a maximize reuse mode that can share I/O registers that are connected to I/O ports through combinational logic. The maximize reuse feature will consider how many registers exist in the fan out from an input port or the fan in to an output port. Now, a single port might have many registers in its fan in or fan out, which would require many shared wrapper cells to fully wrap the port. If the number of fan in and fan out registers of a port exceeds a certain reuse threshold value, a single dedicated wrapper cell will be used for that port. So to specify the reuse threshold, you will need to specify using the set wrapper configuration -reuse threshold, and specify the threshold to be either 0 or positive integer. Let's take a look at an example where the reuse threshold was set to 3 or higher. In this input port example, the port A has been associated with 3 input registers. Therefore, after core wrapping insertion, the tool will convert each of these internal registers into a shared core wrapper. Similarly, for this port Y, the 2 output registers associated to this port. Therefore, after wrapper cell insertion, these 2 registers will be converted to shared wrappers. A feature available for dedicated wrapper cells is to insert clock gating on the clock line that driving dedicated wrapper cells. This will help lower non-wrapper mode power usage.
To enable this feature, specify set wrapper configuration -gate dedicated wrapper cell clock enable. What this does is it turns the wrapper cells off when not in use. The clock gating logic will always use integrated clock gating cells, and you can use this app option to specify a specific clock gating library cell to be used. Fusion Compiler can also insert integrated clock gating cells to disable the clock to unused scan and wrapper cells in wrap-OF and wrap-safe modes. To do that, use the set wrapper configuration -gate cells option. You can specify existing CG option, which will modify existing clock gating cells for the clock masking functionality and will not add new integrated clock gating cells with gating logic to the clock tree. If you specify OR, the tool will modify existing clock gating cells, then will augment with the required clock gating cells and masking logic. These clocks are gated by signals from the test control module by default. If you want to control the clock gating with ports instead of from the TCM, specify set DFT signal -type core cell clock control or wrap cell clock control. You can specify which cells to be added to the input wrappers and which cells to be added to output wrappers by using the set wrapper configuration -input wrapper cells or -output wrapper cells option. In order to use this flow, you must enable maximize reuse. The argument is a tickle list. If you're using collections, use the command getObjectName to convert this collection back to a list. Note that in this flow, there's no check on whether the objects that you have specified are valid cells. Let's talk about the interaction of core wrapping and multi-bit cells. Designs that use multi-bit cells can be core wrapped. In the maximize reuse flow, the multi-bit registers associated ports can also be used as share wrappers. For best results, you should configure and enable maximize reuse core wrapping before performing multi-bit banking. So the recommendation is to specify core wrapper maximize reuse prior to running Compile Fusion to initial map. This will inform the multi-bit banking algorithms that maximize reuse core wrapping will be performed during DFT insertion, and multi-bit registers built from single-bit registers will be separated between input registers, output registers, or core registers. Next, let's talk about multi-voltage flows in Fusion Compiler DFT. Fusion Compiler DFT supports scan insertion in multi-voltage flows. By default, the tool will not mix cells from different voltage or power domains onto the same chain. If you have enabled voltage mixing or power domain mixing, though, Fusion Compiler will insert the required level shifters or isolation cells automatically according to the power intent description if the resulting scan path does cross voltage or power domains. Here's an example of the effect of enabling voltage or power domain mixing and crossing. By default, the tool will not allow voltage mixing or power domain mixing. If you have enabled power domain mixing, then cells from two different power domains are allowed to be combined into one scan path. Similarly, if you have enabled both voltage mixing and power domain mixing, then both scan path 1 and scan path 2 traversing different power domains or voltage domains will be allowed. Reusing existing multi-voltage cells. Fusion Compiler DFT will reuse an existing level shifter or isolation cell if they are on a scan path. So let's say in this example, I have an existing level shifter that is on the functional path that's already driving a different cell of different voltage. After scan insertion, the tool will branch out from the same level shifter for the scan path. Preview DFT will print information about multi-voltage along the chain by printing power domains and voltage information next to the registers, similar to how it prints clock information or clock domains. Fusion Compiler DFT synthesis works with your multi-voltage specifications written in UPF to create multi-voltage clean designs. Both scan synthesis and core wrapper insertion configurations allow flexibility for you to define multi-voltage specifications. DFT insertion by its nature may add new punch ports and registers to your design. Therefore, an incremental multi-voltage specification in UPF format may be needed to specify changes and maintain electrical correctness. These could be port-specific UPF strategies or retention strategies on DFT registers. Regarding multi-voltage strategies on newly punched ports, the goal is to ensure isolation strategies apply to DFT paths and prevent new isolation violations. The two ways to achieve this: you could either specify the source and sink on each domain, or you can specify using diff supply option. Both of these will automate the UPF specification for newly added DFT ports, and will also prevent insertion of redundant isolation cells. Here's the flow for power-aware core wrapper insertion. The tool will check the multi-voltage legality of wrapper cell location before insertion. The tool will also check during scan synthesis the legality of tapping points before making a connection. Once DFT has been inserted, you can add additional UPF constraints on the new logic that is being introduced by scan synthesis. Optionally, you can run the command create MV cells after this DFT insertion to get a multi-voltage clean design. The compile fusion -from initial place command, however, does invoke multi-voltage cell insertion based on the updated UPF. Here are some of the features of heterogeneous scannet support in Fusion Compiler. First up is the tool will split the load from a heterogeneous scannet into homogeneous nets to avoid electrical problems. Connections will be split to drive loads with the same supplies. The tool will follow these guidelines for splitting the connection. It will fork the connections with the same load supplies as close to the loads as possible. It will fork the connection with different load supplies as close to the driver as possible. The tool may share existing net segments to make scan connections, and the tapping point may be different from the original driver pin. The tool will pick a UPF legal tapping point to avoid electrical violations. To summarize this module, we have discussed core wrapper flows. We talked about the core wrapper modes of operation. We talked about the two different types of core wrapper cells. We have discussed the way to configure wrapper cell insertions. And for multi-voltage, we have talked about how does Fusion Compiler DFT handle designs with different voltages.
Welcome to the concluding module of Fusion Compiler DFT Synthesis course. We have covered quite a bit of material over the course, so let's summarize what we have learned. In modules 1 through 4, we described the basic steps in the scan synthesis flow. You learned how to declare the scan interface signals and create a test protocol, running the DFT-DRC command to check for DFT violations, as well as debugging DFT violations using the Fusion Compiler GUI. In modules 5 through 8, you learned how to fix common DRC violations in RTL. You learned how to insert test points. You performed top-down scan synthesis flow to obtain balanced scan chains. We talked about multi-mode scan partitions to insert multiple scan architectures, as well as performing a bottom-up hierarchical scan synthesis and getting balanced top-level scan chains. In modules 9 through 13, you learned how to export files after scan insertion for downstream tools such as place and route and ATPG. You learned how to insert on-chip clocking to perform at-speed testing. You learned how to insert